You know that feeling when your phone battery dies? Or when you see an old rusty gate that's just falling apart? Well, what if I told you the very same invisible force is behind both of those things? Today, we're going to pull back the curtain on this unseen engine, electrochemistry. Okay, so take a smartphone battery, a rusty old pipe, and a shiny gold-plated watch. I mean, what could they possibly have in common, right? One powers your life, one is, well, it's literally crumbling, and the other's a piece of jewelry. But here's the crazy part. They are all, and I mean all, running on the exact same scientific principle. It's this elegant hidden connection, and we're about to uncover it. All right, so here's our game plan. We're going to start with the absolute core idea, what I'm calling the great electron exchange. Then we'll look at how we can actually harness that energy. After that, we'll see what happens when that energy goes wild, think rust. And finally, we'll see how we can use the same science to protect and even beautify the world around us. Let's get into it. All right, first up, the great electron exchange. And seriously, this is the foundation. If you get this, you'll get everything else we talk about today. It's the key that unlocks the whole thing. So what is electrochemistry? Don't let the big words scare you. It's really just the study of how chemical reactions can get tiny little particles, electrons, to move. And guess what we call a whole bunch of electrons moving together? Yep, that's electricity. It's kind of that simple, but it's also incredibly powerful. Okay, so the actual process that gets these electrons moving is called a redox reaction. And redox is just a mashup of its two parts, reduction and oxidation. Now, the important thing to remember is that these two are a team. They're like two sides of the same coin. You can't ever have one without the other. It's a package deal. So how does this work, this electron dance? Well, it's a perfect give and take. You've got one substance that gets oxidized. All that means is it loses electrons. And at the exact same time, another substance gets reduced by gaining those same electrons. It's a clean handoff. One loses, one gains. A perfect transfer every single time. Now, I know, keeping oxidation and reduction straight can be tricky, but don't worry, there's a super easy way to remember it. Just think oil rig. It's a mnemonic. Oxidation is loss, reduction is gain. Oil rig. Seriously, burn that into your brain. It's going to be your best friend for understanding all of this. Okay, so we know how electrons move. Now for the fun part. How do we actually capture that energy? How do we take this wild chemical engine and tame it to do useful stuff for us? Let's dive in. I mean, this is the billion-dollar question, right? The question that literally changed the world. If chemistry can make electrons move, how do we build some kind of container, a box, to capture that flow and use it to, power things? Turns out, the answer is surprisingly clever. And that answer is the galvanic cell, or, as you and I call it every single day, a battery. Yeah, that's all a battery is. It's just a really smart device that keeps the oxidation and reduction parts separate. This forces the electrons to travel through a wire to get from one side to the other. And that trip they take through the wire, that's the electricity we use to power our phones, our cars, everything. So let's build one, real quick, in our minds. Imagine you have two separate containers, right? Each one has a strip of metal in it, sitting in some kind of liquid. Now, you connect those two metal strips with a wire. Boom. You've just created a highway for electrons. But there's one more piece, and it's absolutely crucial. It's called a salt bridge, and it connects the two liquids. Think of it like a traffic cop, making sure the charges stay balanced so the whole reaction doesn't just grind to a halt. Now, those two metal strips, they have special names. The one where oxidation happens, the one that loses electrons, is called the anode. It's the negative terminal. And the one where reduction happens, the one that gains electrons, that's the cathode, the positive terminal. And hey, remember our old friend oil rig? This is where it really comes in handy. Oxidation is loss. That happens at the anode. Reduction is gain. That happens at the cathode. See? Easy. And check this out. This isn't just theory. If you build one of these with zinc and copper, a classic setup called a Daniell cell, you get a real, measurable 1.10 volts. Now I know, 1 volt doesn't sound like a lot, but that little spark of power, that controlled electron exchange, it's the fundamental building block for pretty much all of modern technology. Okay, so we've seen how to control this electron engine to do good things. But what happens when that engine just runs wild, totally uncontrolled? Well, that's when we get corrosion. It's kind of the dark side of electrochemistry. You know what I'm talking about, right? You leave your bike out on the rain for too long and it gets covered in that ugly, flaky, reddish-brown stuff. That's rust. And rust is just corrosion in action. It's the exact same redox reaction we saw in a battery, but this time it's happening spontaneously. And we don't want it to. The metal is just giving away its electrons to the oxygen in the air and slowly turning into that brittle mess. And certain things just poured gasoline on the fire. Moisture, heat, even acid rain can speed up corrosion. But a huge one is salt. Think about it. Why do cars in northern climates rust out so much faster? It's the salt they put on the roads in the winter. That salty slush basically creates a superhighway for this unwanted electrochemical reaction to happen, and your car pays the price. So, if corrosion is just electrochemistry running amok, a natural question is, can we use our knowledge of electrochemistry to fight back? Can we actually fight fire with fire here? And the answer is, absolutely, yes, we can. This brings us to our last section. We're going to see exactly how we can turn the tables on corrosion. It's time to put that unseen engine back to work for us, and in some pretty cool ways. So, have you ever heard of electroplating? The easiest way to think about it is like a battery running in reverse. Instead of a chemical reaction creating electricity for us, we use electricity to force a chemical reaction to happen. And what does that do? It lets us put a super thin, perfect coating of one metal onto another. It's like giving an object a custom-made suit of armor. And once you start looking for it, you'll see electroplating is absolutely everywhere. That shiny chrome on an old car? Electroplated. The gold or silver on a piece of jewelry? Electroplated. It's used for everything from making things look beautiful to making them last longer, and even making electronics work better. It's an incredibly versatile tool. And plating isn't the only trick up our sleeve. You can do simple stuff, like just painting something to create a physical barrier. But the really clever solutions use electrochemistry. Take galvanizing. That's when you coat steel with a layer of zinc. The zinc is more eager to corrode, so it acts like a bodyguard, sacrificing itself to protect the steel underneath. For really big stuff, like underground pipes or the hull of a ship, they use something called cathodic protection. They literally attach a big block of a more reactive metal that just gets eaten away over time, taking one for the team to protect the main structure. So, when you boil it all down, what's the big takeaway here? It's that everything, from the battery powering the device you're listening on right now, to the rust on an old nail, to the methods we use to stop that rust, it all comes back to one fundamental process: controlling that great electron exchange. It really is the unseen engine that drives so much of our world. And that just leaves us with one final thought. We've figured out so much, but this story is far from over. Think about it. We're constantly demanding more and more power from smaller and smaller devices. So the question is, what's next? What will the next great electron exchange look like? How are we going to power the future? It's an exciting thing to think about.